Jai Hind everyone. My name is Shan Kumar Singh, B.Tech second year Computer Science and Engineering, a student of Madan Mohan Malviya University of Technology, and this is the last part, third assignment of my computer organization and architecture subject. Our today's topic is cache mapping, and in this video we are going to cover the following topics. First of all, we will be doing the revision of cache memory, which we have studied in the last video as well. Next, we will be discussing about cache mapping and its type, and then we will be discussing those types in detail. The types include direct mapping, associative mapping, set associative mapping. We will be discussing numericals as well as how these mapping are actually done within the process. So, let us first start with the revision of the cache memory. So, what we have discussed earlier was that cache memory is something between the CPU as well as the main memory. Uh, why is it there? Because it is faster and smaller in size. And I gave an example also in previous video about having all the important books in your study table instead of your library, so that it can be accessed easily. So yes, cache memory is used to reduce the access time. Now, we have studied earlier as well that the modern computer systems have multiple levels of memory, and there is an hierarchy within those level of memories as well. So the CPU would be trying to access the memory in the fastest possible way. So, in context of the cache memory, we discussed earlier how that level looks like. First of all, we have a CPU which inherits data from the L1 level of cache, which is taking it from L2 level of cache. Similarly, L3 of cache, and further the main memory. Going up the order, the speed increases as well as the size decreases. Right, like the closer this memory is to the CPU, the faster it is. Cache memory is something which is placed between the CPU and main memory, and it just reduces our the memory access time. Let me note it down. Reduce memory access time. Cool. So cache memory stores the frequently accessed data and instruction, and like instead of accessing the data directly from the main memory every time, we are storing in the cache whatever is required frequently. We are storing it in cache, and then accessing the CPU would access it through cache. Now, how does the CPU performs this task? We have discussed in previous video as well. Let us revise quickly. Like consider CPU requests some data. Requests some data. So what would happen? The data would be checked in the cache, like if it is available or not. Now, if data is found in cache, it is called cache. If it isn't found, it's called miss. Now we all know what would happen if if the data is found, we would just it would just return the data, and the execution would be performed. In case the data is not found, we would go to the lower level of the memory, that is, we would fetch the data from main memory. Cool. So yes, in case of it, just return that data. While in the case of miss, we would try to look for the data at the lower level of the memory. So fetch data from main memory. Right. So this is how a CPU requests data from cache. If it is available, it is a hit. If it is not present in the cache, then it is a miss. Right. So yes. Now we also studied about cache performance, where we discussed some basic definitions, which was first of all cache hit. That if data is found, it is a cache hit. If it isn't found, it is a cache miss. Then we got some formulas like hit ratio, which means total number of times hit ratio which means total hits by total number of time we try to access the memory. So total memory access. Similarly, we got something called miss ratio. Miss ratio was total miss upon total time memory was accessed, which was also equal to 1 minus hit ratio. Since there is only two possibilities, either a hit or a miss, therefore miss ratio is equal to 1 minus hit ratio. Similarly, hit ratio can also be written as 1 minus miss ratio. Then we discussed about the average access time. Average access time was equal to the hit ratio into hit time plus miss ratio into miss time. But yes, since we have revised our cache memory, let us now move to the next topic, the main crux of this video, the main topic of this video, which is cache mapping. Right, cache mapping. Huh. Now, first of all, let us try to understand why cache mapping is needed. Now, we all know that main memory is quite larger in size than that of cache memory. Why? Because main memory comprises of more number of data blocks, while a cache memory would be comprising of fewer blocks. So, like, what should be our strategy? Our strategy should be that whichever main memory block is there, which should be used to store the data of the cache location. What I mean to say is that where should we store the data of a cache memory? So this is what we call a cache mapping. As I stated earlier as well, the cache mapping is divided into three types. Uh, Before that, let me just write the basic meaning of cache mapping. Like, what we are trying to do is we are trying to answer that which main memory block should be used. Block should be used to store in which cache location. So, like, now this strategy, whatever strategy we will be making, this would be called as cache mapping. Right. So, in a layman term, we can say that cache mapping is something which defines how the blocks of main memory would be mapped or placed into the cache memory. Like, how are we storing the data blocks of the main memory into something, into a cache memory, right? So yes, we have three major types of mapping techniques. Three mapping techniques, which are first and the foremost, the direct mapping. Next, associative mapping. Associative mapping. And last is set associative mapping. Now, we would be discussing these techniques individually in detail. Let us start from the first and the most important one, which is direct mapping. Direct mapping, and as the name suggests, it would be involving mapping the uh, blocks from the main memory directly into the cache memory. But how are we doing this? First of all, there is a concept of something called as a cache line. Right. Now, what is happening is that the block of main memory would be placed in some specific line of cache. We will be discussing it in detail right now. But first of all, let us try to understand direct mapping more in more simpler terms. First of all, this direct mapping is one of the simplest and most commonly used cache mapping technique. So it is simplest and most commonly used cache mapping technique. Cool. Like now, uh, what exactly direct mapping is doing? Let me write in double cuts. What is happening is that each block of the main memory can be placed in only one specific line of cache. Right? Like we are taking a block of main memory and are placing it in a specific line of the cache memory. Right? So each block of main memory can be placed in in only one line of one specific line of cache. One specific line of cache. Like how would be doing this? So it is somehow similar to a concept of hashing, which we often study in data structures. But yes, uh, let us write the formula that how are we directly mapping, like how are we determining that which main memory block is going to be present in um, which of the cache blocks, right? Which of the specific line of the cache block. So we get a formula. Formula is that the cache line would be determined as the main memory block number, memory block number mod the number of cache lines, the total number of cache lines available. Cache line. Now, whatever remainder we are getting after doing the mod of this expression would give us a integer, and we would be storing that the main memory block in that particular line of cache. Like let us try to understand what we are implying here with the help of a question. Let me just pause the video to write the question. Right. So we are having a question here where we are given a system in which the main memory consists of 16 blocks while the cache memory contains of 4 lines. And now we are required to just directly map these main memory blocks into the cache memory. Now the available 4 lines could be written as cache line 0, cache line 1, similarly 2 and 3. Right? So there are 4 possibilities where the main memory block can be stored. However, we have 16 blocks to be stored. Now let me just name those main memory blocks as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Right. So we have 4 cache lines, we have 16 main memory blocks. So the formula says that whatever the main memory block number is, you should take it and mod with the total number of cache lines available. So number of cache lines is 4, and starting from the first main memory block, what we would be doing is we just make a table for easy representation as well as understanding the creation and the cache line. Right, so first of all we take the block number 0. We have 0 mod 4. 0 mod 4 would give us 0. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, we would be performing the same operation for each of the memory block. Now let me do it firstly. 1 more 4 it's 1, 2 more 4 it's 2, 3 more 4 it's 3, 4 more 4. Now 4 divided by 4 is like 4 divides 1, or sorry, 4 divides 4, we get quotient as 1 but remainder is 0. So again the cache line will come as 0. So you see, we are trying to roam within the total available cache lines only, with the from 0 1 2 to 3 only 4 available cache lines. Similarly, 5 mod 4 would give us 1, 6 mod 4 would give us 2, 7 mod 4 as 3, 8 mod 4 again 0, 9 mod 4 1. Right. Completing the table, we have 10, 11, 12, 13, 14 as well as 15, where 10 mod 4 would give us 2, 11 mod 4 would give us 3, 12 mod 4 would give us 0, 13 mod 4 would give us 1, 14 mod 4 would give us 2, 4 would give us 3. Right, so we have successfully mapped all the available main blocks into the given cache lines. Right, so 16 main blocks are like main memory blocks are um, directly mapped to the available 4 cache lines. Right. Like what is happening that the cache line number 0 is getting this block number 0, block number 5, block number 5, block number 8, as well as block number 12. Right. So cache line 0 have blocks 0, 4, 8 and 12. Similarly, cache line 1 would have blocks 1, 5, 9, 13. 2 would have blocks 2, 6, 10, 14, and finally 3 would have blocks 3, 7, 11 and 15. So yes, now here we have understood the concept how direct mapping actually works, but we need to see the problem which is arising here is that a single cache line would be storing a single block from main memory, but here we are getting 4 blocks at the same time. This is what we call the conflict problem. The conflict problem. Right, so from the question we have gained the idea about a new topic. Now this is actually the major drawback of direct mapping, as it leads to conflict mess. What exactly is a conflict mess? Like we have seen in this question as well that different main memory blocks are being assigned to a single cache line, right? So in such cases what happens is that whenever CPU requests the new block, the new block replaces the previous block and the previous block is lost, right? uh, for example, let me just show you here. Consider there is a main memory block numbered 63. Now I am storing it in a cache where I have 10 lines. So the formula says that you need to do 63 mod 10, which would lead to 3. Right. So when block number 63 goes and gets stored in the cache line 3. But now the CPU is requesting. CPU requests block 93. So again, it must be stored in the cache block. Uh, Using this formula, I again get cache line number 3. So what happens is as soon as it is requested and the block 93 is mapped to the cache line, the block 63 would be replaced by block 93. What happens? Block 63 replaced by block 93. Right. So what I wanted to store in my cache memory so that I could easily retrieve it when I would be requiring it further in my execution or the operation gets replaced because something else which have the same remainder after dividing it from the number of cache lines has the same value, right? So this is actually a major drawback and this is called conflict problem. Now, since I have missed block 63 here, which was replaced by block 93, this would be called as would be called as conflict miss. Conflict miss. Now, uh, what uh, this was a disadvantage in the direct mapping. Now let us discuss how do we whatever we are storing in the cache line. How are we writing its address? What is the structure of the address? So our next topic is the address structure in direct mapping. Address structure in direct mapping. Cool. Now, in a direct mapping, we divided the address structure into three parts. Three parts, namely, first being the tag, second being the line. Line refers to the cache line. Third being the offset. Offset or often called word. Okay. So first of all, what is the tag? The tag would identify the tag would identify which main memory block, which main memory block is currently stored in the particular cache line. Next is line. As the name suggests, this field would determine which cache line should be accessed for finding that main memory block. Right. So line refers this field would determine which cache line should be accessed. Next, we have our offset, or what we call bold. And this will specify that like which word inside the block is required. Like the block might contain various words, so which block, like which word the block is, which word of inside the block is required. Cool. So this field would specify which word inside the block is required. In the previous lecture as well, as far as I remember, I told you that the data transfer between the main memory to cache memory often takes place in blocks, while the data transfer between the CPU or the registers to the cache memory takes place in the form of word. So whatever word we are looking for inside the block is being specified by this offset. Right. So this was the address structure. Now let me just take the previous example. We were having 63, right? Let us do the address breakdown of this data element. So first of all, while doing the direct mapping, what was happening was that we were taking a mod of it and we're getting 3. So yes, one thing which is very clear is that the cache line would be 3. Now the remaining thing, which was 6, this would referred as 10, right? So in direct mapping, direct mapping, tag is equal to 6 and the will be equal to line equal to 3. Good. So this data element, this block from the main memory would be stored in the cache line 3. Now, how would the CPU look for this data? So now the CPU is not going to like match the cache line or something else. What it would do is it would try to find the tag. Now, consider the CPU request 63 block. Request block 63. So, like the cache would start comparing the tags. A tag of 63 is 6. So if a tag matches, we say that there is a cache hit. Okay. If the tag matches, we say there is a cache hit. And again, in case it doesn't match, then it is quite clear that the data element is not to be found in the cache memory, and we would be required to move down a level, one more level, to look for it in the main memory. Now this is called as cache miss. Cool. Right. So here we have discussed about direct mapping in quite detail. Now let me just note down the advantages and the disadvantages of direct mapping. Right. So advantages of direct mapping. First of all, this is some simplest form of mapping technique we have. Right. So again, therefore it comprises of very simple hardware. I'm sorry. Right. Yes, so since it's the simplest form of mapping technique, therefore it comprises of a very simple hardware. From here we derive that again it would be comprising of a very low cost, so it is quite feasible and therefore is generally used. Again, therefore it has a fast access time and being simple, it is easy to implement. But the biggest drawback, and um, which we understood with the previous example as well, was about conflict misses. So disadvantage. Very first disadvantages: high conflict misses. High conflict misses. Next is poor cache utilization. I would explain it with a very small example as well. And frequently used blocks may be replaced by each other, as we have seen an example previously also. Frequently used blocks may replace each other. So, what does poor cache utilization means? Consider 10 cache line system, and now the number of blocks which are called by CPU be 10, block 20, block 30. I'm adding it as block 40, and so on. Or similar type of blocks are called, but majorly those blocks are called where somehow the formula always gives us the remainder as 0. That means that cache line 0 would be uh, storing and replacing these blocks. But the thing is that there were 9 other cache lines as well, and some of them may not get utilized, right? So therefore, a cache line is getting replaced multiple times. The blocks are getting replaced multiple times, while other cache blocks, for example, be it 1, 2, 3, they other cache lines just they are not used, right? So they are present there, but they are not used, and we also know that the cache memory are small in size. So we should be trying to have the maximum output. We should try to have maximum utilization out of it. So this is also a disadvantage with direct mapping, right? So next mapping technique in the list is associative mapping. Associative mapping. We would be trying to understand associative mapping in detail here. Uh, right. This mapping technique is often called amongst the most flexible mapping technique, and here is why. Like the concept which associative mapping is using, and I'm writing it in double quotes, is that any block of main memory, any block of
पढ़ लिए
main memory
पढ़ लिए
can be placed in any cache line. Cool. Like what does this mean? It exactly means what it is written here, that we can arbitrarily give any block to any cache line available. But then how would whenever the CPU requests some data block, how would we how would we be fetching it? Like in previous example, we were having a formula which was quite similar to what we study in data structures, the method called hashing. Direct mapping was quite similar to that. But here, there isn't anything sort of a formula. Uh, what we would be doing when the CPU would be request CPU would request us a data block is that we will be simultaneously checking all the cache lines, and if the data block matches, that is our cache hit, else it would be our cache miss, right? So yes, let me write it. This is the most flexible mapping technique. Why? Because there is no fixed location at all. There is no fixed location at all. Right, sorry for the interruption. There is no fixed location at all. So yes, how are we fetching or searching for that data block in the cache memory? We were looking for it simultaneously. What is the structure? So structure is quite simple. We will be having our address, which will be storing with the data. This is the structure. So as I told earlier, whenever the CPU would request, whenever the CPU would request the data, what we will do is that the requested address will be compared with all the cache addresses simultaneously. And yes, if the match is found, it's a cache hit. Else we would be like moving back one level down to main memory, and that would be a cache miss. Right, so let me write it. When CPU requests data on requested address is compared with all cache addresses simultaneously. And yes, if a match is found, if a match is found, it is a cache hit. Now, it is exactly performed. No, that particular process, the process performed using associative memory. From here only the name of associative mapping comes, associative memory, or the content addressable addressable memory. So uh, let me just take a very small example so that we can understand what exactly we are doing in associative mapping. So in this example, consider a cache having 4 lines. Right, cache having 4 lines. So we have 4 cache lines, and CPU is requesting the data blocks from the main memory. It, so consider they are stored as any random memory block. As let it be block 20, 1, 2, 3, have block say 15, 51 consider, block 63 say, block 1. Cool. So here the 4 cache lines uh, have been storing these main memory block. Now if a CPU requests block 63, then voila, it is here at cache line number 2. What happens is that cache checks all the entries simultaneously. Now match would be found. It would be a cache hit, and it is in cache line 2. Wait, but what happens next? It was having only 4 lines of cache, and now it is required for another main memory block to be stored in the cache line, the cache memory. So here comes the problem with the associative mapping. Uh, the cache is full and a new block has arrived. So for storing the new block, some block must be removed, right? So the replacement policy in associative mapping, think there can be various replacement policy, but let us discuss like one general property or policy. But before that, let me just write why the replacement policy should be brought. It is because if a cache is full, a new block arrives, and new block arrives, then we must remove an existing block. Remove an existing block. So this would be requiring some replacement policy. Now there can be multiple replacement policy, one of which is the first in, first out replacement policy. Right. So as the name suggests, the policy is first in, first out. So whichever block was entered first in the cache would be removed first, right? So the block that entered cache first is removed first. Quite cool. So um, let me give a very brief example of it. Consider there is a cache order of something like PQRS or any order. Now, this order means that P was inserted first, then Q, then R, then S. it was four-line cache system, right? So cache was having only four lines. So if a new block is requested, or if a new block arrives, of course the space should be made, some existing block must be removed, right? So as soon as a new block arrives, according to the first in first out policy, replacement policy, the first in block, which is the block P, would be removed. So we would be removing block P. Order would change as QRS and QRS and let's say a new block named T. So this is the change. This is the new block. Yes. So after removing P, we would be adding T. Yes. So this was about associative mapping. Now let us discuss its advantages as well as disadvantages. First, advantages. Now, biggest advantage is the drawback which we were facing in the previous mapping technique, and it is that in case of associative mapping, there is no conflict misses. Why? Because like we are not bound by some fixed formula. We are just issuing or storing the main memory block according to wherever it wants to get stored, and whenever a new block arrives, we just remove some block, make some space, and then add the new block according to any replacement policy which we follow, one of which we discussed previously. Right. Again, another drawback which we were facing in direct mapping was that there was no proper utilization of the cache memory. I gave an example as well, but here all the lines, if the maximum capacity is required, then all the lines can be utilized. So it has a better cache utilization, and therefore it has a higher hit ratio. So these were the advantages of associative mapping. Let us discuss the disadvantages. Disadvantages. Again, previous example was quite simpler in nature and therefore was cost effective. But the associative mapping is not so visible. It's a bit more expensive. So it has an expensive hardware. And yes, we would be having a complex comparison circuit. Why? Because we are required to simultaneously match the addresses to get a cache hit. And yes, therefore it has a higher power consumption. So it is not economically more sound than the previous example, but yes, at least it has a better utilization, right? So that some that like balances out at some sort. So yes, it has higher power consumption. Now yes, since it is a bit expensive, therefore we generally don't use fully associative cache for large caches, right? So because of these disadvantages, fully associative caches rarely used for large caches. Used for large caches, right? Right. So in the order we have our next mapping technique, which is the set associative mapping. So far we have discussed the direct mapping and the associative mapping, and we have found that both of them have some advantage as well as some disadvantage. But here we come to the third mapping technique, and it is derived from the previous two techniques. So it uses concepts from previous two techniques, from both of the techniques. We can consider it as a combination of, it is a combination of the previous two techniques, which are direct mapping and associative mapping. What happens is that the cache lines are divided into some number of sets. Now each set can contain multiple lines. Like what we having previously, that we were having some system of having four cache lines. Here what we would do is that the complete cache memory would be divided into some number of sets, and then those lines would be, like, some lines would be given to some set, like one set, other lines to some other set, right? So the set can contain multiple lines, right? So concept here is cache divided into sets, right? And each set contains multiple lines. Quite good. So what happens is that the main memory block would map to some specific set, like considered through some formula, but inside that set they can occupy any line. So the first part comes from direct mapping and the second part comes from associative mapping. What is happening? Let me write it again. The main memory blocks would map to some specific set, but inside the set, they can occupy any line. They can occupy any line. How would we be mapping them to any set? We would be using the formula we used previously in direct mapping, through uh, like through that mod formula. Cool. Let me just take one example. So let us consider a two-way set of associative cache. What does a two-way set associative cache means? It means that it will be comprising of two sets, right? So let us consider that the system is having four cache lines. So system having four cache lines, and it is a two-way set associative. Therefore, total number of sets would be total number of sets would be 4 by 2, it's 2. So we have a set 0, we have a set 1. Set 0 would comprise of cache line 0, cache line 1, and set 1 would comprise of cache line 2 as well as cache line 3, right? So inside the set we can store the memory block to any of the cache line, but first of all we need to map the memory block to some particular set, and for that we would be using that simple formula, which is the block number of the memory block mod total number of sets. In this case it is 2. For example, let me just take a random block 6, right? So the set number would be given as, for this example only, would be given as 6 mod total number of sets, which is 2. 6 mod 2, it comes out to be 0. So the block 6 would be mapped to set 0. Now inside set 0 there are two options, either line 0, cache line 0, or cache line 1. Now here we don't need to like apply any formula, and we can just store the block 6 to either line 0 or line 1 as we wish. uh, it is a healthier practice to store it first so it can be stored easily. But there is no hard and fast rule for this. It can occupy either line 0 or line 1. So yes, let us now study the address structure address structure for set associative mapping. Address structure. There is nothing much different from direct mapping. What is that? What comes new is our concept of sets. First of all, we are having a tag. Then instead of line, we are having a R set, and then the offset or word. Right. So tag would help us to identify the block as it was helping us in direct mapping. Identify the block. Set would map to the particular set. Set selects set. Now inside the set, we would be like simultaneously checking all the cache lines, and if we get that particular data item which we are looking for, then that is a cache hit, and else it's a cache miss. And word again would select data within the block. Yes. So let me just first of all write that advantage and the disadvantage for set associative, and then we will look for a numerical as well. So advantages, first being, again, it is reducing conflict misses. Why? Because it is a combination of both the mapping techniques. So yes, since it is inside the set, we are not using any formula, we are just using the concept we used in associative mapping. Therefore it has a better performance in comparison to direct mapping. The performance in comparison to direct mapping, right? And yes, therefore it has less hardware cost in comparison to the other option, the other combination, associative mapping. Cool. But with advantages, it has some disadvantages as well. Since again it is combination, as I am speaking again and again. Advantages. It is a combination. Therefore, the hardware would be slightly more complex in comparison to that of direct mapping. So hardware is slightly more complex. Slightly more complex. And yes, it is slower than direct mapping. Why? Because inside the set, even though we are mapping the set through some formula, but inside the set we are simultaneously looking all the cache lines for finding the data item. So it is slower than direct mapping. So let us do a question. Let me just pause the video while I note down the question. Yes. So here is our question. Question states that the cache memory has 8 lines. So we are having a computer system where cache memory has 8 lines, where we are having 8 cache lines, and it is a two-way set associative cache. It means that the we can say the set would be comprising of 2 cache lines, right? The main memory has 16 blocks. The 16 blocks would be required to be stored here. Now the question asked is how many sets are present in the cache, and then we need to determine that wherever the following blocks would be stored in which set only. So yes, so first of all, let us determine the number of set. Number of set would be given as, first of all, the number of cache lines. by how much set associative it is. So it is a two-way set associative, we will be dividing by 2. So we will be getting it as 8 by 2 as 4 sets. So we are having 4 sets. Let us name them respectively set 0, 1, 2, 3, and they would be storing cache line 0, 1, 2, 3, 4, 5, 6, 7. So these 8 cache lines are stored within 4 sets. The first answer is 4 set. Now next we need to find where the blocks would be stored, like in which set the blocks would be stored. Block 3, block 7, block 12. So for this we have our formula states that first of all in which set they would be mapped. So this formula states that the set number is equal to the block number mod number of sets. Cool. So for the first condition, the block number is 3, number of sets is 4, so it gets stored in set number 3. For the second block 7, block is 7, number of sets is 3, so it again gets stored in set 3. Similarly for block 12, it's 12 by 4, it's cool. So we have a set 0 storing the block 12, a set 3 storing a block 3 as well as 7. Cool. So each set comprises of 2 cache lines. So block 12 can be present in either of line 0 or line 1, and 3 and 7 also can choose any of the available cache line, either 6 or line 7. Now in case there comes some other block, say block 11, and again it is given to set 3, then we would be following some sort of replacement policy. Any of the block would be removed first, and then the new, like the space would be made for the new block to arrive. So in this way we have completed our lecture of cache mapping. Whatever we have studied, let me just remind the topic as well. First of all, we revised the cache memory, then we try to understand what cache mapping is and why are we doing it. Then we delve deeper into the different types of cache mapping. First of all, we gave a lot more time to direct mapping. Then we studied about associative mapping as well as the set associative mapping. Now in direct mapping we were using some sort of formula, but we were having some conflict issues. In associative mapping we were not using any formula and were just like storing the memory block in the cache line as our wish without any specified or any prior rule or something. So at least we were able to counter the conflict problems. But here the hardware issues, as the circuitry was more complex, therefore it was not quite used for we can say large caches. Then we came up with the combination of direct mapping as well as the associative mapping, which is called set associative mapping, in which we divided the cache into some sets, and the sets consisted of multiple cache lines. Now the sets were determined, the sets were mapped using some formula, but inside the set we can just store the main memory anywhere in any cache line. Right. So this was all about this video. This was Shan Kumar Singh, roll number 2024021 065.